So, welcome. Today we are going to discuss down with very deep convolutional neural network. So, in the last one with VGG nets and then with Google nets, you have gone down from the version of 16 layers, 19 layers and subsequently to 20, 23 layers over there. Now, here is where we are speaking down about hundreds of layers. Okay. Though we will start with very simple networks over there, but then these are networks which are available for 100, 200 and 250 plus kind of layers, and then so you can sort of imagine like between going from your VGG net to Google net, the amount of increase in operations which you had to face down, though there was a slight decrease in the total parameter space as well. Now, here if you go down in hundreds of depth, then what will be the total number of parameters which you will have to learn, as well as what will be the total compute complexity. Now, that is something to be really curious about and inquisitive about. So, bringing back from what I had discussed in my earlier lecture on Google net is here I would be covering down two specific ones. So, Google net was the award winning CVPR paper in 2015. The next one was ResNet or the residual network, which came down in 2016, and subsequent to that we have the densely connected networks DenseNets in 2017. So, we are going to cover down ResNet and DenseNet over here. Now, residual network or ResNet as it is known down as. So, what it does essentially is that it implements something which is called as a residual pipeline. Now, we have this really well written down diagram over here, much more easy to recognize as compared to Google net. Now, I never drew the diagram, so you have to pardon me for that. It was a direct takeaway from the papers which we have been referring to, and that is the reference which given now. Now, here it's easier to look at it. We'll come down to even deeper, like what happens as we keep on going deeper and with them. Now, here what you essentially do is there are two parts of it. You see this factor which is called as a size. This is basically x and y sizes. So, input whatever you give over here is the ImageNet standard size image, which is 224 into 224 into 3. So, that is an RGB image of 224 cross 224 sized given as input over here. Now, we have convolution with 7 cross 7 kernels. There are 64 such kernels, and the convolution is with a stride of 2. Okay. So, this is what you get down over here. Now, since if you have padded convolutions and with a stride of 2, so obviously the output size over here is 112 cross 112, okay, and the receptor field is 7 cross 7, pretty big, and this is what we are keeping it down pretty much standard from Google net. We are keeping it pretty much standard from LeNet itself, and then where you had the first major receptor field which was really wide at 7 cross 7. That goes down from the aspect that majority of these images on ImageNet and for our simple images in day to day life which we are using now, this kind of 7 cross 7 is what has a significant role, and it can encapsulate most of the appearances of objects coming down over here. Okay. Now, after this we have a max pooling by a factor of 2. Okay. Now, due to this max pooling, this is going to get reduced by another half. So, my 112 cross 112 sized image gets now reduced onto 56 cross 56. Okay. It's no more an image, it is basically a volume whose spatial size is 56 cross 56 and the number of channels is 64. So, it is 56 cross 56 cross 64 which is available over here as an input over here. Now, what we do is we do a first is a 1 cross 1 convolution with 64 channels. So, essentially the output of this first layer, which is 1 cross 1 convolution and 64 such channels, is going to lead me to a similar size matrix. The output matrix is still going to be 56 cross 56 cross 64, but you need to remember that these 1 cross 1 convolutions have actually ended up mixing all the properties along one particular pixel location across all the channels, and that is the interesting fact which comes down over here. Now, subsequent to that we have a 3 cross 3 convolution with 64 channels, and then again a 1 cross 1 convolution with 256 channels. Now, this is the place where your number of channels actually explode out. Okay. So, here we did local mixing across the different channels. In the next one it is where there is a spatial mixing, spatial and across the channels mixing on 3 cross 3, and subsequent to that I just have 1 cross 1 which is again for mixing along it, but then mixing along one particular pixel location, but you are increasing the number of channels over here. So, this is where your information is actually getting spread apart. Now, you see this solid line which comes down over here, and that is something which is called as a residual connection line. Okay. So, what it essentially does is it takes it all the values which comes down over here. So, whatever was the values available over here and just adds it onto these connections over there. Okay. Now, addition is as in plain and straightforward addition over there. One thing which you should ask me at this point of time, I was yeah, but then we are not asking on a real time. It's already recorded. So, here a question which should pop up is that see, the spatial span is pretty simple, it's 56 cross 56, okay, and here nowhere we are doing a downsampling or a strided convolution or a max pooling, nothing. So, the output spatial size is still 56 cross 56, but the number of channels has definitely changed out. Now, here we had just 64 channels, here you have 256 channels, that is 4 times that number of channels over here. So, what we essentially do is that we just do a 1 cross 1 convolution and then upsample it out around over here. So, that so that you have and this whatever comes down over here is a tensor of size 56 cross 56 cross 256. Okay. Now, from there is what goes down over here. Now, here again you have 1 cross 1 convolutions and getting down to 64 channels. So, your total number of channels over here, which was 256, that again gets reduced to 64, then 64, then again a similar one. But then this pipeline over here had 256 channels. So, you can actually populate that back over here, and the spatial size is still the same because there are no strides or there are no max pooling and anything. So, now it happens like this and comes down over here. Now, here your output is 56 cross 56 cross 256, great. Now, you do the next level of convolution over here, where you have 1 cross 1 convolution with 128 channels and a stride of 2. So, obviously, the size has decreased over here. So, the output over here is going to be 28 cross 28 cross 512, but then here you had 56 cross 56 cross 256. So, you need some sort of a change over here. So, this is a these dotted lines over here is what conveys that over here you are going to do another kind of a convolution with and then change it down from 56 cross 56 cross 256 to 28 cross 28 cross 512. That's a learnable block as well over here. So, this is how it keeps on going down. So, whenever you have a dotted line, it means that there is some sort of a downsampling in the convolution as well, and otherwise it does not. Okay. Now, there are these different kind of blocks. These are called as CFG 0, CFG 1, CFG 2, CFG 3, and now if you want to make 50 such layers, then what you would do is at layer number 3, 4, 6. So, what you would do is you would put down this blocks subsequently at these particular layers over there. Okay, this what is that layer number which corresponds to that, and then you can get down this 50 layer, 101 layer or 152 layers. This is what it comes down. Now, on the block side over there, if we are trying to look directly into what happens with the residual, then this is what it looks like. So, the actual paper which implements it out is something like this, that you have your input coming down, and this is that part of the residual. That was those pipelines which we were looking down. On the other side is this convolutions which are going down. Now, technically we had a convolution, then you could do a batch normalization, then a ReLU, and then a convolution and a batch normalization. You add everything and then do a ReLU. Okay. Now, there was also another option which have been provided by people who are other than the authors. Now, here what they did is they, instead of doing a batch normalization over here, they do a batch normalization after the addition, and then so the addition and the batch norm, these locations are just changed. So, that technically means that not just this part of it is what is batch normalized, but something which comes from here as well as from this output together you add and batch normalize, and in fact that makes a more plausible sense, because now your batches do not have a tendency to overshoot. Even if there is an overshoot coming from here, you would still be normalizing it out over there. Now, the other one is what they did is they had all of these batch norms and everything, but they removed out this last ReLU. So, they are just different ways of making it less compute intensive, because it sits really deep. You have seen that it can go down to 152 layers as well. Now, getting back from there, this was the first layer where an interesting thing was observed. So, if you are trying to create a deep network with just 18 layers versus if you are trying to create a deep network with 34 layers. Now, what would typically happen is, and then what they do over here is these solid lines which you see, they are all training errors, and the thin lines, the bold thicker lines are for training errors. So, the bold one in cyan, this kind of a blue like color is what is for 18 layers. The one on red is for 34 layers. Now, technically whatever we were saying till now is that if you are going deeper and deeper, then your errors should be lower and lower, okay, for the same kind of a baseline. So, that would mean that if I am at a given learning rate and in condition, then this is with one learning rate, these are definitely with lower learning rates over there, and that is how you get it down. Now, definitely over there when I am saturating somewhere over here and then changing the learning rate in order to come lower and lower, at this point of time my cyan curve should actually have been above the red curve or the red curve below, because this is an error. So, my error with a deeper network should be lower than my error with a shallower network, but that is not happening over here, it is very different. Now, this is what got people really intrigued into it, that what was the reason. And now for ResNets, what they figured out is one of the major reasons why this was happening is that your input is not getting conveyed. You need a part of the input to also be conveyed. Now, definitely there comes down another question is if you have this kind of a very deep network, you had 152 layers over there. For GoogleNet, which was just barely about 23 layers or something, you are already facing the problem of decaying and died down gradients. Now, how will you train this whole thing? Now, this is where there is a clue left down. You see these extra pipelines over here. So, whatever is the gradient, this comes over here, it passes through this one. So, there will be like 1 and 2. So, there will be say 10 power of minus 2 change which comes down by the time. So, if over here it is unity gradient, here it becomes 10 power of minus 2. But then when you are passing it down through this other pipeline, that does not have any attenuation on it, because there are no gradient multiplications with activations over here. So, this is still unity gradient, whereas that gets added to 10 power of minus 2. Now, this is what is going to influence down everything. So, technically if we look over here, just by virtue of all of these kind of pipes which are existing over here, the exact value of gradient can actually be carried forward back till over here, and that is interesting. So, now you created a network where not just your forward pass could put down the same component of input and carry it down till the end, but as well as your gradient from the end in its exact value can actually be carried down for influencing this first node over there, and that means that you do not have a vanishing gradient problem over here. So, there were two birds in one single shot that you could hit down. One, you actually have a part of your input going down and merging to create your output, which is really great because they are not able to do that. You had your wide receptor fields and everything over there, but a part of the input was never getting merged onto the output. The next which you could do was that your gradient as such from the output could be back propagated into your input, making it really easy to learn over there. Now, that is the great thing which happens with a ResNet, and in essence because of that purpose you would see that residual networks are the first one which demonstrate that a deeper network actually gives you a lower error as compared to a shallower network. So, ResNet 34 in its training is what is giving a lower error than the 18 layer residual network, and you can also see that the validation error for the 34 layers goes even below the training error. Now, that is curious, because that is something which we have always desired to have, that whatever be the training error, that should have sort of be the upper bound on my error to be achieved in validation, and that is what I see for residual networks coming down. Now, it is interesting that whether is it only for ImageNet kind class of data sets, or do you have it for other class of data sets, that is something I leave it to you. So, we will be doing experiments only on ImageNet and CFAR kind of data sets over here to show it down on a small toy example, but you can take all of these back on your learning exercises and do it on even bigger data sets as well. Now, from there comes down my parameter spaces and the total number of operations which comes down. Now, technically for a 18 layer what you have is these kind of convolutions over there, and then you can what you can do is pretty simple. You just need to multiply the parameters over here. These are the parameters which define down your kernels over there, and then just do it and you will find out what comes down as a total number of parameters which you will have to learn down in your model. We will be exploring more deeper into the next model when we go down in terms of versus the number of parameters over there. And in terms of number of operations, you see that it takes down 1.8 into 10 power of 9. So, this is 1.8 billion operations for a 18 layer, and by the time you are at 152 layer, it is 11.3 into 10 to the power of 9. So, 11.3 billion. Now, from 1.8 billion to 11.3 billion, that was almost like 8 times of a rise which goes down. But from 18 to 152 is the total number of layers which you have traversed. So, you know how deep you have actually gone down over there. Now, that's sort of like scales out, because 18 into 8 would give you a number which is quite close to 152 maybe. So, that is an interesting point of an observation over here. Now, after that is what we have is what is called as a DenseNet. So, immediately when you had residual connections and everything coming out, so people thought that while in a residual connection what you do is that the output from the first layer is what is connected to the second layer, but then you do not have long order dependencies, which means that can this output over here also influence and connect down to my next one. So, that would mean that can I have output from any layer connecting down to all the subsequent layers and influencing it out. So, that is what a DenseNet comes down. So, if you look carefully through it, what it does is you have your first set of filter banks over here, you have your batch normalization ReLU and then a standard convolution, then you feed it down to the next bunch of your filter banks. Now, this output is added to the output over here. Next, you have your bunch of filter banks, and then whatever comes down as a output over here, you would see that the output from the first filter bank is what is added, as well as the output from the second filter bank. Now, each filter bank's output has the same color code as in the filter bank. So, the red ones are from the first, the green ones are from the second, the violet ones are from the third, the yellow ones is from the fourth, and then over here from the fifth you have the orange ones, and you see that everything is connected to everything. So, this is a very dense flow of information, and then back when you traverse from here, you would see that all of these get added down, and there is obviously an original form of the gradient which gets back over here and modifies all of this. Whereas, you also have these tapped out gradients, like the gradient which is coming from here, as well as the gradient from here, as well as the gradient from here, which also comes down directly and adds it down. So, that means that I have in some way created a mechanism of pushing down gradients from all the other ways and getting it down. Information forward flow is also there, as well as while I am modifying, I am also getting down gradients coming down from each of them, and then this is a very densely connected network which works out, and that is the name for it. Now, where it goes down is it is more complicated than the earlier ones over there. So, you have your output flow sizes, block sizes and everything given down, and then you can sum them up totally. So, in the next labs where we do this ResNet and DenseNet, we will be looking into the total number of parameters and doing their whole summations and finding out how it works out. Now, finally, is where I would come down as a concluding note over here. Now, what you see is quite interesting. So, we showed in the ResNet that if you have residual connections available over there, then the deeper you go, the lower is the error, or the better is the accuracy which you would go down. So, that would bring you to the point that yes, with residual connections, deeper networks are really good, and I could train down deeper networks by not even having the vanishing gradient problem, and not even trying to have these auxiliary classifier arms which were otherwise present down in my GoogleNet in order to get out of this vanishing gradient problem. In fact, that is also solved out. The problem and not the problem, but the interesting fact is that what is the order of parameters, and then how does it fare across in both of them. If you look down, say at ResNet 152, the total number of parameters which you have is somewhere around 60 million, 60 into 10 power of 6. Okay. So, this is 6 into 10 power of 7, that would make it 60 million. A similar order network or even deeper is DenseNet 161. Now, DenseNet 161 is what positions itself somewhere over here. Okay. Now, the number of parameters it needs is much lesser than the number of parameters which will be needed down by ResNet. Okay. What is even more interesting is you go down towards DenseNet 201, which is actually a more deeper model, because you have 201 such convolution layers. But then the point is that your number of channels over there per layer has been reduced in DenseNet 101, and what that leads to is that for a deeper network, you actually use lesser number of parameters. And now, this model uses just 20 million parameters. You go down to 152, which is just 50 orders less than that, but this order uses 3 times more number of parameters as compared to this one. And if you look into the validation errors over here, you would see that DenseNet 161, which has the lowest validation error achieves something with 30 million parameters, 30 million learnable parameters, whereas ResNet 152 at the same kind of a validation error would require 60 million parameters, which is double that. Now, more the number of parameters, obviously you need more number of samples to learn, and you need larger number of epochs as well to learn. So, at any point of time it gives out that these kind of dense connections from everything to the other one is where it makes it really interesting. Now, on the other side of it, we look into the total number of compute versus the error which comes down. Now, for a given error vertical, so somewhere over here we are sticking down to the same one. So, you have your DenseNet 161, which would be taking down 15 billion flops, 15 billion floating point operations. At the same error level, you have ResNet 152, which would be taking down 22.5 billion operations. Now, going away from 15 billion to 22.5 billion operations, there is almost 7.5 billion more operations which is needed. So, that is technically 50% surge over here. So, whatever is needed over here, we need 50% more on top of it. So, half of 50% of 15 billion is going to be 7.5 billion. You add that one, you come down to this position. Now, you see that there is a significant increase as you are going down with just residual network as compared to DenseNet, and this is what the authors have also brought down over there. You have much more deeper network, you have lesser amount of compute, you have lesser amount of parameter space, and this is a clever engineering which you will have to do. So, while that is really something which I would leave it out to you, and while we go down in subsequent more advanced topics, but then this being just a beginners over here, this was to give you an idea that deeper networks are not necessarily the most compute intensive or not necessarily the most say parameter intensive networks as well. You can build up deeper networks which can converge much faster, take lesser number of operations to converge down, as well as they would even have a smaller parameter space available to them. So, that is with what I would end down this one. And on the take home message, my only point is that you can go down through this particular book on deep learning, and the other, because these networks are pretty new, so they are not in the book. Two of these networks are even beyond the date of publication of the book. So, I would suggest that you actually find them out, and then they are freely available on CVF, on the CV forum, on the Computer Vision Foundation online open access points, and just go through them. They would be much more interesting. So, in the subsequent two lectures, we will be having a hands-on session on understanding DenseNet and ResNet, and that is where we will do a pen paper calculation versus actual parameter calculation, as we have done for earlier AlexNet and Google Nets, AlexNet and VGG nets as well. So, with that we come to an end on this one, and thanks.